Not hearing any. Normally, I would have Kent Richardson introduce the What's Up speaker, but it's my pleasure to introduce Kent Richardson as our What's Up speaker. And if you have questions, remember to use the chat to ask questions and keep your microphones off. Thank you.
Thanks. And Stephen, thanks for the earlier plug for the need for some speakers. I'll get right into it here. I've got to share a screen. Not sure how to, I'm not getting what I want. There. Now, are you seeing that?
No.
No. No.
No.
Whatever app you're using, you have to explicitly share that. You know, like if you're using PowerPoint or something like that, you have to share.
Well, yeah, when I go to share content, go back to Zoom. When I do share content, it gives me this thing. It says screen broadcast, Zoom, start broadcast.
Share screen.
Okay.
That worked.
Yes.
Well, whatever you did, we could see your screen. That's working.
I'm sharing screen. Okay.
Yeah, it's working.
All right. Now I got to get back to it.
Yep. We see your desktop.
There. Okay. Do you see PowerPoint?
Yep. Yes, we do.
Okay. Here we go. Okay. Fast radio bursts. Many of you may remember about 2.5 years ago, Dr. Casey Law from UC Berkeley came to the club general meeting and talked to us shared a lot of information about fast radio bursts. And even prior to that, our presidents, Will Roberge, and then later Steve, had some information in the President's Corner in the newsletter back around the same time period. At the time Dr. Law appeared, there were about 50 known fast radio bursts, or FRBs as they're called. Today there's 120 that are cataloged, and 111 of them are verified. They use an arsenal of telescopes. And by the way, you mentioned the closure of Chabot. I hate to say it, but there are a number of observatories around the world that are closed now for the same reason. Aperitif is in the Netherlands. The BSA LPI-1, that's actually LPI, is in Russia, and it's at the Pushchino Observatory near Moscow. And we've got Parkes down and Utmost and ASCAP down in Australia. Utmost is, that stands for Malangalo, I'm getting this, Malangalo Observatory Synthesis Telescope in Sydney. And then they upgraded it, so they called it Utmost. ASCAP is the Australian Square Kilometre Array Pathfinder in West Australia. Arecibo in Puerto Rico. DSA 10 is in the Owens Valley here in California. Green Bank is in West Virginia. I'm sure you're familiar with that. And I'm not sure how this last one is pronounced. I'm going to call it Keim, only because it's in Canada. That's the Canadian Hydrogen Intensity Mapping Experiment. I'll talk about some notable FRBs. This one is, first of all, a mention of the nomenclature. The number represents the year, 2001, the month, July, and the day, the 24th. And they're normally called FRB, a 6-digit number. This is referred to as the Lorimer Burst because Duncan Lorimer at the Parkes Observatory assigned a student to go through some archive data from 2001. He did this in 2007. And they discovered the information that produced the identity of this fast burst, fast radio burst. There were some earlier ones. I'm sure they were found through some other digging around in the archives. This one is about 3 degrees from the small Magellanic cloud. Okay. This one in 2012 was picked up by Arecibo. It's the first repeating, highly sporadic, but repeating fast radio burst. It's highly polarized, and it's got 500 times the strength of any other that we have found to date. In 2018, Dr. Law participated in the development of 2 studies, 2 papers that were published in 2018, the year after he was here. This one in 2015 was identified by the Russians, but they didn't report it until 2018. So it wasn't immediately recognized as being the second repeating fast, easy to say, FRB, but it was the actual in time was the second one. There was one of 9 that they reported. FRB 180301 has a spectrum that the Breakthrough Listening Project has identified as being very positive. If you don't know about breakthrough listening, it's kind of allied with SETI. They're looking for signs of extraterrestrial intelligence. Now, this long, strange number is really the nomenclature that's been used since about the middle of 2018. And this was found by, or discovered by Keim. And they have been able to identify most of their objects in the Sloan Digital Sky Survey. So it's FRB 180916, and then the .J and numbers identifies the SDSS object. This is a very unusual repeating one. It was the 4th one found. You probably read about it in the news because it has a 16.35 day period, very precise. And the way it operates is it has about 4 days of spewing out bursts and then 12 days off, then 4 days on and 12 days off in 16 1/3 roughly days sequence. FRB 180924, discovered by with the use of ASCAP, is a first repeating traced to a source, a galaxy about 3 and 3.6 billion light years away. Once ASCAP picked it up, that's an array type of telescope, they had to use the Very Large Array, Gemini in the Atacama Desert, and the Keck telescope to pinpoint exactly where it was coming from. FRB 18 1030, let's keep the page. Another one discovered with Keim, and most likely comes from NGC 3403, based on their analysis. FRB 181112 has been localized to a small galaxy, and it was found that it had an unusual lack of effect after passing through the halo of an intervening galaxy. FRB 190523 is a non-repeating FRB which has been localized to a galaxy nearly 8 billion light years away. So what's causing all this? There's a lot of speculation, even more so than what you might have heard from Dr. Law 2.5 years ago. There's no generally accepted explanation. Any or all of these are entirely possible. I won't try to go into the details of any of these unless there are questions. Anyway, here's my sources. If you use FRBcat.org, that is the complete catalog that I got those numbers that I told you before. In some of the other listings, you'll find the same FRB is being identified with 2 different numbers because it was observed on 2 different days. They weed all that out with our FRBcat. And that is my story.
You could unshare now. Thank you, Kent, for that. And now, any questions? Go ahead and type them into the chat. I saw one from Nathaniel, who would like to see the list of possible causes again.
Would like to see that again? Okay. Wait, I gotta share again first. Okay, now. I've got to restart the, unfortunately I stopped the PowerPoint. I have to start it over again. Okay, let's just do this.
Anyone else has questions?
Yeah, here's the first half of the list. Maybe Nathaniel can take a picture of the screen at his end. And then here's the second half of the list. If you go to a search on fast radio bursts, look for the Wikipedia entry. This is where I got most of my material, and they're updating it quite frequently, adding new references, not much new information in the body of it, but they're adding new references and citing new studies and documents almost daily. Okay, do we need that anymore?
Good. We have a bunch of questions here. Axion mini clusters.
That one I didn't look up. I was going to, and I didn't have time. I'll be happy to, but I can't do it at the moment.
I know. An axion is a subatomic particle.
Right. So a mini cluster of subatomic particles. Some of this stuff is held in. However, there was one that has had 3 reports now that provide some support, and that's magnetars, which are highly magnetized neutron stars.
And do all the FRBs have the same frequency spectrum?
No, they're not all the same frequency. They tend to be in the range around 800, 850, but they've been below 700, and some found up higher, like 1100, 1400 maybe, but typically in the 800 range. Okay, I answered what's a magnetar. That's a highly magnetized neutron star.
Any other questions?
Nathaniel's doing research on axions. You're quite welcome. Megahertz, not kilohertz, megahertz.
Anything else?
You're welcome.
Well, with that, we're going to go ahead and I'm going to have everybody thank Ken for doing the what's up.
I might say for those that would hesitate to do a what's up, it's a lot easier from the comfort of your home than standing up before the group in a dark room. And you can have all the refreshments you need while you're doing it.
Yeah, and Ken, give yourself a pin while you're doing that.
Yeah, I've already got one.
Okay.
Thanks.
So with that, we're going to take a 10-minute break. We'll be back. So enjoy your virtual snacks. You know where the restrooms are, hopefully. We'll be back at about 7:50. Give us a chance to get things set up for our next speaker.
Steve, shall I try sharing my screen? Is this a good moment? Test that?
Yes, please go right ahead and
Okay.
bring it up, and I'll unshare mine.
Okay. Let's see. All right, can you see that PowerPoint slide okay? I'm not hearing, you're muted, Steve. I don't know if you're trying to talk to me.
I'm sorry, I didn't catch the question.
Now I'm hearing you. The question is, can you see my PowerPoint slide okay now?
Yes.
And do you see it as a just the slide, or are you also seeing the sidebar of small slides? I'm not used to this mode. I don't usually use PowerPoint. I use something else, but I decided to use it for this.
You have the sidebar, so you need to.
You have the sidebar. That's odd. Huh.
Check the chat.
Sorry, check the chat. Okay. PowerPoint, yeah. PowerPoint, yes. Full screen, no. Yeah, it's odd. It's because I am sharing my full screen on my laptop, so I'm confused about why that's not working. So let me try again. Let me try sharing again. Let me turn off the share.
Looks good now.
Now you see just the slide?
No, you need to do the start the.
Probably I need to start. I know. I probably need, before I share, I should start it as a.
Yeah, I think you just want to go to the slideshow menu or just hit F5.
Right on.
Yeah, it's funny because I did this, I practiced with it earlier, and it's just once I go to slideshow, it no longer lets me, I can't go to slideshow before I share. It's very odd. So I have to share it first. Actually, let me just share my desktop. Maybe that's the easiest way to go.
Can you
Rather than
click
share.
on the slideshow icon on the top?
Yeah, let me, you know what I'm going to do? I'm going to share my desktop rather than the PowerPoint. That may do the job. And then I'll go to, let's see, share that. And then I'll go to full screen. How about that? Slideshow. There we go. Did that do it?
Yes, that did it.
Okay, yeah, the trick was to share my desktop rather than the PowerPoint. Okay, great.
We'll get started in just a few minutes.
Sure, thanks.
Steve, this is Pete. I liked your comment about everybody knowing where the bathroom is. Have to think for a minute about it.
Hmm.
Okay, why don't we go ahead and get started? It is my pleasure. Typically, I would have Dick Flask introduce our main speaker, but Dick had another commitment. So it is my pleasure to introduce Professor Cool, a native of New York City, an undergraduate from Yale. And after a brief diversion in medical imaging and electrical engineering, she found astronomy, her true calling. She completed her PhD at Harvard, came to California for a postdoc at UC Berkeley. She's now at San Francisco State University. And it's my pleasure to introduce Adrienne Cool, spying on star clusters.
Thank you so much. It's a pleasure to be here. I really appreciate everybody coming to this strange format we're having to use. I hope everybody is hanging in there these days and doing okay. I've taught quite a few classes using Zoom, but I haven't, done something quite like this. So hopefully the technology will behave and you'll be able to hear me. Please do. I am going to bring up the chat window. Please just, let me know, unmute yourself and shout out if you can't hear me or you can't see me or whatever. I'll try to keep an eye on the chat, but hopefully others can help with that. Steve, if you could help with that, feel free to interrupt me with any question that you see fit from the chat. So as Steve said, I'm at San Francisco State, and it's a great place to work. And we have a combined physics and astronomy department, and people may or may not know, but a pretty sizable department, 12 physicists and astronomers, and typically about 15 or 20 undergraduates graduate from our department each year, and 5 or 10 graduate students, sometimes more. This is just a list of undergraduates and graduate students, sort of 50-50, who've worked with me over the years on the research that I'm going to tell you about, different aspects of it. They, fade a little bit into the background, but are never forgotten. It's very fun for me to see where they wind up. I have students who are now professors at other universities. I have students who are working at Cal Academy, Exploratorium, planetariums around the country, students who are now community college teachers, high school teachers, doing all kinds of different things. And it's really a joy to me to see what everybody does after they leave San Francisco State. I'd say about maybe a third or half go on to graduate programs. Another third or so become teachers of some sort, informal or formal teaching, and a few go on and use their computer skills or other skills to work in industry. So that's just a little bit about some of the things in our department. What I wanted to talk about today is I realized with the 30th anniversary of Hubble having just gone by, and my own career in astronomy really having been very closely tied and affected, I should say, by Hubble. I wanted to say a little bit about that at the beginning, show a few slides, and then I'll talk about the research my students and I have been doing, my collaborators and I have been doing for the last few years, and just pick out a few specific things that illustrate the kinds of things that we're looking for and interested in. And I'm going to end with a little astronomical perspective on the fact that Earth Day just passed, and a little bit about maybe astronomers' role in thinking about things we face on Earth right now. So a little bit of history for me. When Hubble was launched back, 30 years ago or so now, I was sitting on the top of, this was deployment the day after launch. I was sitting on the top of this mountain, Cerro Tololo in Chile, working on my PhD thesis. And it was a wonderful place to be. You can see, just for fun here, you can see Alpha and Beta Cen, and the Southern Cross here, and the large and small Magellanic Clouds. And next to the small cloud is a globular cluster. It's so compact you can't tell it's a cluster there. But I was on this telescope, the 4 meter, and we were trying to find binary stars in globular clusters, a particular kind of binary star that I'll talk about in just a minute. And in particular, we were looking for them inside of globular clusters. I'm sure all or most of you have looked at globular clusters through your telescopes. The particular, they're very fun to look at, I think. I'm probably biased, but I think they're pretty cool looking. The particular one that I was looking at long ago, and I still continue to look at in various ways intermittently, is a relatively paltry little cluster called NGC 6397. It happens to be the nearest one. It's in the southern hemisphere in the constellation Ara. It happens to be the nearest one with a very, very dense center. And that's kind of why we were interested in it, because we thought that it was possible that globular clusters actually might manufacture binary stars. The hypothesis had been put out there that when the cluster's central regions become very, very dense, and I'll say more about that later, that it might be that stars might come close enough together to capture one another and create binaries where there hadn't been binaries before. And so we were looking for these binaries, and the problem is they're really faint. And so this is what the center of that cluster looks like. Very good, high quality CCD image taken with one of the telescopes on Cerro Tololo looked like this, and good seeing, good conditions. You can kind of already tell that, gosh, I'm probably missing some stuff. Things are pretty blurry in here despite, very good seeing. And so this is where I was in 1990 when Hubble was launched. As many of you may recall, when the tests were first made and the first images were taken with Hubble, there was a large shock went through the astronomical community because it turned out that the images we were getting looked like this rather than like sharp dots that we were expecting to get. And it turned out, and I won't go through all the details, but it turned out that although the mirror had been ground to an unprecedented smoothness, it was ground to the wrong shape. And the result was this crazy looking stellar images. And I just wanted to mention, because I think it's kind of a funny situation, that although it was like that, you notice how you can still see many, many faint stars here. And it turned out that I had been using images like this, ground-based, high-resolution images, to look for these binaries, and I hadn't found a single one yet. And we've been looking really hard. As soon as Hubble was launched, my advisor and I got time the very first cycle with Hubble. We got images that looked like this, and that made my thesis. We found what we were looking for, even though it had this crazy-looking point spread function, as it's called. I always find that kind of amusing, that even with that, very alarmingly poor stellar image, it was way better already than what we could do from the ground. Okay, fast forward 3 years, I finished my thesis in November of 1993, and the following month was the first servicing mission when they were going to try to essentially repair the mirror. And of course, they weren't going to repair the primary. The primary was going to stay how it was, but they were putting special optics into a new camera that was going to be put on that would correct for that aberration in the primary mirror. And so I was absolutely glued. Oh, and I had gotten a postdoc at Berkeley with a guy by the name of Ivan King, who was kind of the grandfather of studies of globular clusters. And he had been working on the Hubble program since its inception and had some guaranteed time on it. And so when I arrived to do a postdoc with him, whether or not that servicing mission was successful would make the difference between, would really affect the next few years of my life and what kind of data I'd be working with. So I was absolutely glued to the TV watching every move the astronauts made. And it was so interesting and fun to watch them, and really impressive, the work that they were doing. Here, I think this is Hoffman is taking the old camera out. This is the wide field planetary camera that produced that image that I showed a minute ago. He was taking it out, and it's like the size of a baby grand piano, and you could just, move it around out there in space, traveling 18,000 miles an hour. It's always impressive to think about that. Here is the slot that had just come out of. They stowed it over here. It is stowed over here, and then waiting, this is the old one, and then waiting in the cargo bay is the new one that they're going to put in. This is the Wide Field Planetary Camera 2. Fortunately, that was a highly successful mission, and this is the result. The image on the right is an image that came out after that servicing mission. And so it was a very, very exciting time to be working in an area of astronomy that really benefited from the incredible, breathtaking spatial resolution that we could achieve, that was being achieved with Hubble. And so, for example, here again is the middle of NGC 6397, this globular cluster in the southern hemisphere that I was working on, searching and searching for these binaries and not finding any. And here is what that same field looks like with Hubble. Now, I'm just going to blink back and forth so you can see. And I'm sure you've seen many versions like this, but I don't tire of seeing how those things compare. And you can see why, if the kind of stars we're looking for are, let me just find one. I know them pretty well, even in this non-color version of the image. Like this star right here that I'm on top of, that happens to be a cataclysmic variable. You can see that's going to be pretty hard to see in that ground-based image right there. So that's the kind of data we started working with. I cheated a little here because this is an even more recent image that I took of it, but the idea is the same. This is the advanced camera that was put on subsequently. Okay, so it's a little bit about how fun it was to get to work with Hubble, and I want to talk now about a bit about the kinds of things that my group and I have been working on, but I did want to just wish Hubble a happy 30th and many happy returns. It's been an amazing telescope in so many different areas of astronomy, and my particular field has benefited from it tremendously. It couldn't have been done. What I do can't be done from the ground at all, effectively. Okay, so what kinds of things have we been doing? Well, like I said, we studied globular clusters, and so just to get oriented here, what are globular clusters? They are these big balls of stars that form a halo around our galaxy. There are many of them toward the center of the galaxy, and then they are dispersed throughout the halo of our galaxy. A typical globular cluster contains some hundreds of thousands of stars, some upwards of 1 million. And the reason I certainly got interested in them is partly that they're just spectacularly beautiful, but also there are a bunch of other reasons. They're extremely old. They're the oldest identifiable objects in the galaxy, having formed before the disk itself formed. And they're an interesting dynamical problem. Like if you have a ball of stars and it's all held together by gravity, what happens? How long is that stable? How long can that last? What happens? How does it work? And the sort of nutshell version of what happens is that they're stable on sort of million-year time scales. But on longer time scales, they don't just stay exactly the same all the time. The central regions gradually collapse, gradually condense and become denser and denser. The outer regions expand. This happens on a time scale on which stars exchange energy, which takes a long time because they don't, even though they look very close together in these images, they're not actually very close together. So it takes a long time for them to actually nudge each other around. And in a way, in fact, some of the early theories, you can think of it as like a ball of gas almost, where each star is like a particle of gas. And if you think about the air in the room, you know, some of the particles are just happening to move very, very quickly. Others move more slowly. There's a range of velocities. Now in globular clusters, that high velocity tail of the distribution of velocities is high enough velocity that they'll actually sail right out of the cluster and not come back. So over time, stars gradually evaporate, we say, leave the cluster. As that happens, energy is carried away, and the inner regions of the cluster tend to collapse. And various theories have predicted, well, you know, if the center becomes dense enough, eventually stars will start glomming together, you get one giant thing, and eventually you get a black hole at the center. And some theories certainly predict that. It'd be kind of a special black hole, because it wouldn't just be the kind of, you know, black hole of a few solar masses that you might make from a single star that exploded. Instead, the expectation is that you might get what's called an intermediate mass black hole, intermediate between the kind a single star makes and the kind that you find in the middle of a galaxy that can be in the millions or even billions of solar masses. The ones inside of globular clusters are predicted to be on the order of a few hundred to a few thousand solar masses, and they're commonly called intermediate mass black holes. Interestingly, none have ever been found yet, at least in globular clusters. They may still be there, but they're not easy to find if they are there. They're making themselves hard to find. People are still looking, but meanwhile, there are questions about, well, will they necessarily form? And that's where binaries come into the picture. It turns out that if there are binary stars present in the cluster, or if the cluster can form some new binaries, as I alluded to before, then those binaries can act as an energy source, essentially, in the cluster center. The binding energy of the binary can be given, the potential energy in there, the sort of binding energy of that binary can be given to a passing star, essentially giving a kick to a passing star. Some of the binding energy is lost from the binary, and then the passing star gets a kick. So really these binaries in the middle act like egg beaters, kind of keeping everybody else moving around, and that can delay the collapse of a core, so-called this gradual collapse that I've been talking about. It can delay core collapse, possibly to longer than the age of the universe at present. So maybe these collapses haven't happened, but there's signs that they have. Sort of a long story. There's a lot of uncertainty still about exactly what is going on. But binaries, at any rate, play a really important dynamical role in globular clusters, affecting this core collapse process, and possibly affecting whether black holes will form. So, just as one example, one of the clusters that we observed a while ago is the biggest cluster in the galaxy. It's called Omega Centauri. You can actually see it. I saw it naked eye from Tucson, from Kitt Peak in Tucson a few years back. It's a really bright object. I saw it out a bus window in Chile. Of course, it's in the constellation Centaurus, so you have to be pretty far south to see it well. This is a cluster for which there have not only been sort of theoretical predictions that there ought to be a black hole, an intermediate mass black hole, but there had been some observational indications that maybe there was one there, based on the velocities of stars, the way they were moving near the cluster center. So just as an example of, well, how do you go trying to find out if there's a black hole in there? One way you can do it is in the X-ray. And so what we did a few years ago now is we pointed the Chandra X-ray Observatory at Omega Cen, and got an exposure of the cluster for about 80 hours. We pointed at Omega Cen for about 80 hours. And this is what we saw. And it's kind of fun to look at an X-ray image, because they look very, very different from optical images. Among other things, you count the individual photons quite nicely. Let me zoom in on this a little bit. Every dot you see there is one photon. And where you see a whole bunch of dots, well, that's where there's a source of X-rays that we can, identify or try to identify. And then the sort of sum total of all the other X-rays is understood to be what's called the X-ray background. Background X-rays from all the active galaxies far away in the universe that, each of which we might get 1 or 2 photons from in one of these exposures. So bottom line is, if there is a massive black hole in there, and it's accreting any gas is falling into it, then before the gas falls over passes through the event horizon, it would heat up, and we ought to be able to see it. That heated up gas would get very hot, and X-rays is a good way to see hot gas. So let's zoom in on this a little bit more. Well, I guess I'm fully zoomed in here. This red circle marks the area, marks the center. So the center of this globular cluster has been measured very, very accurately from the other image I was showing you, and other methods as well to sort of cross-check it. And that central region, there's like no sign of any excess of X-rays. There's a couple of individual photons within that circle, but it's not at a higher rate than just the general X-ray background. So we concluded there's no detectable source of X-rays at the cluster center. If there is a black hole in there, it's really quiet, and unusually so. So we haven't ruled out a black hole, but we've been able to say if there is one in there, it's an unusual black hole. So that's just one example of something that we did with, in this case, not with Hubble, but with one of the other space observatories that we've been making use of over the last few years. Let me come back to having said something about black holes and not finding them in this one example. So back to NGC 6397. Just a kind of case study in how did we go about looking for, or how have we gone about looking for binaries. And I'm going to talk about 2 kinds. We've looked for lots of different kinds of binaries in here actually, but I'll mention a couple kinds. So here this is actually a WIF-PIC2 image from that repaired, that first repair, after that first repair mission. And I like this image because we took images through multiple different filters. And then one of the folks at STSCI actually created this combination, this color version of the image as a part of a press release at the time. And I was always really happy with how well it showed the different colors of the stars. And just to say something about, I mentioned that there's a very dense cluster. To get a feeling for that here is one light week. So in the middle of this cluster, stars are not light years apart, they're light weeks apart. Okay, that's still pretty far, right? It takes, light goes a long way in a week or even a day, but really it's a lot denser. It's about a million times more dense than the solar neighborhood is the density of stars in this cluster. So we were interested, as I said, specifically in trying to figure out if there were binaries that contain the 2 most common kinds of stars in globular clusters, which are white dwarfs, burned out low mass stars, which are extremely common, and low mass main sequence stars, normal sun-like stars, which is lower mass because even the sun in a globular cluster like this would have burned out already because these things are so old. One kind of binary you can go looking for are the kind where there's a main sequence star and a white dwarf, and they're close enough together that the main sequence star is actually spilling material from its surface onto the white dwarf. And those are what are called cataclysmic variables, and some of you may have observed some of these. There's some really cool ones that vary in brightness a tremendous amount, SS Cygni and other examples. We can see in the night sky with a small telescope. So that's what we were looking for in the cluster. So how do you find them? I mean, there's a lot of stars in here. You could go looking just in the optical, and we certainly did do that, but we also made use of X-ray imaging. And originally it was pretty low spatial resolution, but more recently we've been making use of the Chandra X-ray Observatory, which has very high spatial resolution. In fact, these, let me just move this. These two images are on the same scale. So I'm just going to blink back and forth. So what this says, basically, if you look at it, is that, let me just put the laser on, let's say this one, somewhere in this vicinity, in this image, is a star that's emitting those X-rays, in all likelihood, unless it's something from behind the cluster. But there's a pretty high, there's pretty high density of sources right near the cluster center, so it seemed unlikely they wouldn't be associated with a cluster. And so what we went looking for is, is one of these stars, does one of these stars have characteristics that tell us, yes, that could be one of those cataclysmic variables? Same thing with, same thing over here. Is one of these stars, and there I just jumped to the one that says yes. And so, yeah, we were able to identify for all 5 of these things with Hubble, we found a star that has exactly the characteristics you'd expect for a cataclysmic variable. Very blue, and I'll show one of these diagrams that you may be familiar with. So here's a sort of artist's rendition of a cataclysmic variable with a main sequence star filling its so-called Roche lobe, filling its gravity well, and there just some materials just spilling over the edge there, and then accreting onto a white dwarf at the center. These diagrams are the measurements that we make to actually check whether anything interesting is going on. And so you just look at the left panel, for example. Here we're looking, this is a so-called Hertzsprung-Russell diagram or color magnitude diagram. On the x-axis is the color of the star, and on the y-axis is the brightness, with the bright stars at the top, faint stars at the bottom, hot stars on the left, and cooler stars on the right. This is the main sequence. These are normal stars. And when we're looking for cataclysmic variables, we're looking for oddball stars, stars that don't look normal, something that's different about them. And in particular, they look bluer in certain combinations of filters, especially. This is actually the wavelength of the central wavelength of the filter in nanometers. So this is up in the ultraviolet. This is a blue filter. And so these stars are putting out a lot of ultraviolet light. They're very faint stars. They're way fainter than the sun. The sun would be up here somewhere on this diagram. I won't belabor the rest of these, but suffice it to say that there's another signature that was important for us to see, which was a signature associated with hydrogen, a feature in the spectrum of hydrogen called H alpha. And when you see that, it's very strongly associated with X-ray emission. And typical of cataclysmic variables. Anyway, so we were able to identify in this cluster these cataclysmic variables, and you can even just barely see. I don't know how well you can see this on your screens, but like this one, you can just barely see that's a slightly bluish star in this rendition. So it's slightly bluish as well, but really, of course, it's from the graphs, not just from the visual here that we identified them. Let me say that. So anyway, so that's one of the things we were able to do with Hubble, and you can see that from the ground, why it was from the ground we, despite a lot of work, we had not succeeded prior to 1990 when Hubble went up to find these things. My thesis advisor had hypothesized that that's what they were many years earlier, but neither he nor anyone else had been able to actually verify if that's what they were. I want to take just a couple minutes to talk about one other thing in this image, and this is actually my favorite part of this. And it's really true of really anytime you use a telescope, and I'm sure all of you are familiar with this, that part of what's fun, right? Maybe you go out on a night with your telescope and you have a plan to look at certain things, and you look at them and they're fantastic. And so that's like, we looked for these cataclysmic variables and we found them, and that was really exciting and fantastic. But equally exciting, if not more so, was the serendipity, things that you run across and you didn't necessarily expect. And so in this image are some other objects that we discovered that were not expected and have provided us a whole new window into the binary star population in the cluster. And so I just want to say a little bit about those. So you can actually see them, they actually stand out in an even more glaring way in this picture if you look carefully. And that is, you can see these sort of bright aqua little little stars. There's one here. You may have noticed there's one over here, and there's one up here. And yet they're not X-ray sources. They're very blue stars. And I'll just mention, in case anybody knows this, you may be looking at these bright bluish green ones and wondering, well, what are those? These actually turn out to be what are called blue stragglers. And if anybody wants to hear about those later, I'm happy to mention. But it was those who had already been known and have been studied further with Hubble since. But it was these really faint blue ones that we were very curious about. What we concluded after some significant study and some looking at their light curves and comparing their light curves to those of the cataclysmic variables is that they were very, very different. And just to say, what do I mean by light curve? I mean, we did some imaging where we took a whole series of images with Hubble, repeated images, and then measured how steady or not is the light from these different stars. Cataclysmic variables do something called flickering. They're constantly varying in their brightness. Sometimes they have big outbursts, like dwarf nova outbursts, which are many magnitudes, but other times they just flicker all the time. These other three stars were very, very steady sources of light. Now you might think, well, maybe they're just white dwarfs. Well, it turns out no, they were too bright. For the color they're too bright to be normal white dwarfs. But what it turns out is that they have all the characteristics you would expect of unusually low mass white dwarfs. White dwarfs made not of carbon, which is the normal thing, carbon and oxygen is a normal white dwarf, but made of helium. And it turns out that you can get a white dwarf made of helium if you interrupt the evolution of a star as it's going up the giant branch, as it's becoming a giant. Its core is made of helium. If you interrupt that evolution before it can ignite the helium and turn it into carbon, if you interrupt that, then you can wind up with a white dwarf made of helium. And well, how do you interrupt the evolution of a giant? One way you can do it is if there's a binary companion, so that when the giant is growing, suddenly it encounters the companion, engulfs the companion. The companion then spirals through the envelope. There's now some friction. So the companion then spirals through the envelope, ejects that envelope. Sounds very complicated and crazy, but this really does happen. There's other evidence outside of clusters for this happening. Spirals in, and then you're left with the core of the former red giant plus this companion star. And so for a bunch of different reasons, we've concluded that that's what these things are. They're binaries where the star that we're seeing is a low mass white dwarf made of helium, and the companion, based on where in the cluster these are, they're very concentrated to the center, which means they're quite massive. That means there has to be a massive companion kind of tying them into the cluster center. We think their companions are heavy white dwarfs. So there they are. Since then, we found a whole bunch more. This was part of a thesis, one of my former graduate students' theses. These are all these weird helium core white dwarfs with binary companions. And the dark blue triangles are cataclysmic variables in the cluster. All these dots here are normal white dwarfs, the carbon-oxygen white dwarfs. And you can see that the helium white dwarfs lie in a different part of the diagram. They're brighter than normal white dwarfs. That's because they're bigger, actually. Okay. So I have a couple more minutes. I want to say a couple things. So that's a few of the things that we've been doing, the kinds of things we've been looking at with Hubble and with Chandra Observatory for the last several years. And really Hubble I've been working with since it was launched, which is a privilege and an honor to have been able to do that. And I wanted to say just a little bit more about that and sort of the privilege of being an astronomer and the perspective of being an astronomer. And that really is in connection with as I mentioned, in part, I decided I want to say something about it because of the 50th anniversary of Earth Day. And of course, I was thinking about this image and why is this such a beautiful image? Well, partly it's like, wow, there's Hubble and it's looking out at the universe and helping us learn all these amazing things. But it's also an incredible image because Earth is there and the Earth is so beautiful, and it shows, our atmosphere so beautifully, this particular image. So in that context, I just a little sort of personal perspective on this. I, over the last few years, increasingly have felt that, here there's so many things happening on Earth, and in particular in connection with climate change, that it's been a struggle for me to think, what can astronomers do? We spend, astronomers and astronomy educators, amateurs, professionals, students, what can we bring? Is there something that as astronomers we can bring to this? And is there some perspective of value that we have that we might help combat this problem? And it dawned on me a few years ago that we really do, and there's, I think, maybe fair to say, responsibility that we have. We have such a, I think, who is there besides, folks who look through telescopes, who do sidewalk astronomy, who teach astronomy, who do lectures in astronomy, who know and think about this all the time. Who of us have more sort of visceral awareness of the isolation of the Earth and the sort of preciousness of our planet, and how very, very, very far away all those other planets are? We're finding planets all over the place. It's amazing and fantastic. But, the next nearest planet, and that's not, it's not going to be a habitable one, is at the very closest out at Alpha Centauri. And that's really, really, really far away. So we need to take care of this one. And so in that context, a bunch of students and I and some fellow faculty member at Yale decided to start an organization. So I wanted to tell everyone just a little bit about that, and ask and invite questions, and invite you to learn more about it and see if it's something you'd be interested in joining. And I'm gonna actually just share, I'm gonna change my screen share for one quick sec. And this will just take a, let's see, new share. I'm gonna get out of this, stop the share. Boom. To try to make this work. Okay. All right. Come on. Let's see. Share. It's done. Done. Oh, okay. Well, I'm having trouble figuring that. So let me just do this instead. Okay. I'll just show a couple pictures from the website, but you can look at it yourself if you like. So we started a new organization. It's about 6 months old. We've got about 420 some members, and including amateurs, professionals, planetarium folks, educators of all kinds, astronomy educators of all kinds around the world. We now have, I think, 28 countries represented, and we're trying to bring an astronomical sort of our perspective to the issue of climate change. So why astronomers? Because we have a pretty unique perspective, and we reach a lot of people. When I love doing sidewalk astronomy, I talk to a lot of people when I'm showing them Venus through the telescope. I teach a lot of classes. Some have hundreds of students. I can bring this in and provide that astronomical perspective on the issue, the sort of crisis that we're facing. Who else besides us knows better than anybody that there's no plan B, no planet B? I think that in the popular press, we're always hearing about new Earths or whatever, and people are searching for other Earths. I think it can get muddled in people's heads that, oh, gee, maybe we just can go somewhere else. No, we can't go somewhere else. We'll learn a ton about ourselves, as we always do from astronomy, but we can't go somewhere else. So anyway, that's a little bit about that organization. This is just some of the folks on the website. There's a listserv that we can all people can share with each other what just ideas we have about ways to communicate about climate change in the context of astronomy. And I can tell anyone who's interested in that more about that. And so, yeah, so if you're interested, let me know, join us, check out the website, see what you think. All right, and that's the end of my talk.
Well, thank you, Professor Kuhl.
Thank you.
And why don't we just entertain questions and go ahead and just unmute yourself and go for it.
Okay, let's do that. Questions. And for the moment, I'll leave up my PowerPoint, but after that, I'm going to take it off because I can't see you guys very well without when I have the screen share going on. So,
Could you repeat again the website for the?
yeah, you bet. Here it is. It's astronomersforplanet.earth. You can maybe see it at the top of the screen there. So it's a .earth site, astronomersforplanet.earth.
If you do have questions, blurt them out.
The helium versions of dwarfs.
Yeah, white dwarfs, yes.
How dense are those helium?
Yeah, that's a good question. They're still incredibly dense, but they're not as dense. They're lower density than normal white dwarfs. That's because, not so much because they're made of helium, but just that they're lower mass. And because they have lower masses, their masses, normal white dwarf in a globular cluster is about a half a solar mass. These helium white dwarfs are more like 0.2 or 0.3, so sort of half as much. And because white dwarfs are held up by this weird quantum mechanical phenomenon called degeneracy pressure, or electrons don't want to be too close together, when an object that's held up by that kind of pressure is more massive, it's actually smaller, and it's less massive, it's larger. And so they have less mass, you know, say about half as much mass as a normal white dwarf, and they're larger, and so they're lower density. But they're still, you know, crazy high density objects. You know, still way.
Thank you.
Yeah.
I have a question.
Yeah.
Earlier you mentioned blue stragglers, I think.
Yes, yes. You want to see, shall I go back to that thing that shows the blue stragglers? I'm just trying to make it on my screen so I can see who's talking here. Yeah, let me go back to, here we go. Yeah, so blue stragglers, yeah, it's quite interesting. In the middle of this cluster, these half dozen objects right here that look sort of bluish green, those are what are called blue stragglers. People have been studying blue stragglers in globular clusters for quite a while, and what it's thought now that they are, and actually been thought for a while, but there's more and more evidence for this, is that they're actually stars where two or more stars have collided and merged. And they tend to the star is rejuvenated as a result. And what I mean by rejuvenated is, let's say you had two stars that were, let's say one star that was running out of hydrogen in the center, or close to running out of hydrogen. Another star comes in that still have plenty of hydrogen left and collides with it and merges with it. Then that material is mixed back up, and suddenly there's more hydrogen available. So the star can then live longer than it otherwise would have. The straggling aspect of these is because they should have already burned out, but they haven't yet. They've straggled along. And why blue? They're bluer than your average star in a globular cluster, certainly of sort of normal stars or hydrogen burning stars in a globular cluster, because they're more massive. Stars of the mass of these stars should have already burned out. So these are hanging around, straggling around longer than they should.
I see, thank you.
Yeah. So just to say a tiny bit more about that, you know, in the galaxy in general, stars never collide with each other. Stars are just insanely far apart. I like to do in my class a thing where I take a candy sprinkle you know, and say, okay, this is the sun, and then another candy sprinkle, here's the next nearest star, Alpha Centauri. How far apart do I have to place these two to make a scale model of the sun and Alpha Centauri in a correct placement? If one is in San Francisco in my classroom, the other one has to be in Oakland, where I live. So they're insanely far apart. That's little tiny candy sprinkles, you know, 20, 30 miles apart. So stars in general do not collide with each other in the galaxy. And that's also why two galaxies can pass right through each other without any collisions between the stars, which is kind of wild to think about. But in globular clusters, the density of stars is high enough that they can collide with one another, and they do. And you can, I mean, it's not hard to predict how often it should happen. Just, you can look at the velocities of the stars, you can see how many, you can check the density. It's really just it's not a hard calculation to make. And they absolutely should collide with each other once every few million years or so. So that doesn't sound very often, it's not. But these things have been around for more than 10 billion years. So if there's a collision every million years, that's thousands of collisions. So, you know, interesting things can happen. And that's also, yeah, go ahead.
Oh, sure. Just a quick question. My only question for the night, believe it or not, and my club members won't believe it, but I just wanted to ask if you mentioned something about wandering stars earlier in globular clusters, and I maybe missed a little something, but how many of these kind of wanderers that are traveling really fast and they seem to be unmoored from any kind of binary or just any fixed place in the orbit of a galaxy or anything like that, how many of those do you believe could come from globular clusters? And I'll take my answer muted.
Oh yeah, so just random high velocity stars.
Yeah.
Oh, that's interesting. You know, the velocities in globular clusters in general are not that high. And so I think, you know, a lot of high velocity stars, like one sees, you know, pulsars, for example, moving at incredible clips, you know, 400 kilometers per second kind of clips, you know, are thought to be the result of asymmetrical supernova explosions. Certainly there could be some such things resulting from globular clusters. The evaporation that I was referring to is a more sort of gradual thing. It's just, it would typically be that the star would just barely exceed the escape velocity of the cluster and just very gradually sail out and just never quite get pulled back in. So it'd be a much more gradual thing. But if there's an interaction, but to say a little more, because I think this is also what you're after, if there's an interaction between a binary and a passing star, it is possible for that passing star to get a big kick if it's just right. And that could then just go sailing right out of the cluster, not just heat it up, but potentially have it sail right out of the cluster. So that certainly can happen. So yeah, if that answers your question.
Dr. Kuhl?
Yeah.
Dr. Kuhl?
Yes.
This is a general question about globular clusters. What's the process by which globular clusters were formed before most of the rest of our galaxy? Why were the, if I understand enough about globular clusters?
So, great question. This is an very active area of research right now. Nobody really knows the answer. I can tell you the broad sort of outlines that we have. And the outlines we have because we can see what trajectories globular clusters are on. So the fact that they're not in the disk means that they're in the halo and on all very random orbits within the halo means that they formed before the gas settled and gas settled into the disk. They formed out of gas as it was collapsing to form the galaxy. And they had to form, you know, before that dissipation occurred so that they were already a cluster of stars that would then just sail right through and keep going on these big, long, you know, eccentric orbits that they're on in all random orientations. So the picture is that as the gas that formed our galaxy as a whole was coming together, that they formed while it was still collapsing before the disk. Before the gas, you know, flattened into a disk. The details of that are not well understood. Another thing that I didn't say anything about that Hubble, has been a really interesting outcome of a lot of work with Hubble is that, especially making use of its ultraviolet capability, is that whereas when I went to grad school, we all learned, and you'll see this in textbooks, probably still to this day, that a globular cluster contains all stars with identical chemical compositions, and that's kind of the lore and and it seemed to be true based on the best color magnitude diagrams, Hertzsprung-Russell diagrams we could make back then from the ground. But now when we make them with Hubble and make incredibly accurate measurements that we can make with Hubble, we find that they're much more complex than that they actually have multiple populations of stars formed very, very early. And it's like no one gets it yet. Theorists are struggling to understand how did these, the detailed formation process of globular clusters. But the big picture, I think, is pretty well understood, that it's from the gas as it was collapsing, they somehow formed. But how is TBD.
Thank you.
Yeah.
Dr. Kuhl, is it a similar process like the Oort cloud that's surrounding the solar system? If you think of the solar system, the planet as a little galaxy, is that the same kind of arrangement?
In terms of what, the structure you mean? Like the Oort cloud being a sphere? Or,
yeah. Yes.
Yeah, I mean, in that sense, yes.
A different process developed by different processes.
Yeah, I mean, that's an interesting question. Yeah. Yeah, I don't know what else to say about that. I mean, the size scale, right, is so
different. Yes.
So very different.
It's just odd that in both cases you have a halo going around.
Yeah, well, I mean, one thing to say about that is, roundness can come from randomness, right? Like the reason that we, for example, think that some galaxies are elliptical or almost spherical is it's thought that that's the result of, mergers of galaxies from many different angles, all kind of mixed together. And then you get orbits in all different orientations. So randomness can lead to sphericalness. That's certainly true for like globular clusters. There's stars on individual globular clusters. Stars are on all different orbits within a cluster. And then globular clusters themselves within the galaxy form a spherical distribution with orbits in all different random orientations. So I think of it as a randomness thing. Okay. Yeah, it's a good question.
Do we think there are planets around the stars in the globular cluster? And if so, I've always wondered what the sky would look like in the middle of the globular.
I did once figure out that, I think I thought about it for 6397 since I worked a lot on that cluster. And interestingly, there would be many, many stars that would be as bright as Venus is in the sky. But it wouldn't be like, the sun is so much closer than other stars. So it's not, even light weeks away makes something, if they're not that luminous, but, as bright as Venus. So imagine having many, many Venuses. I mean, that would be pretty cool.
And do we think there are planets around some of those stars?
People have looked. There have been searches that have not been successful in finding them. But I have to say that until, a lot more has been done, I'm not going to believe that they're not there. The reason partly for that is there was a paper, I remember reading this when I started grad school. In 1987. There was a paper written in 1980 that said there are no binary stars in globular clusters. We've looked and they're not there. Well, they looked at some things, but there's a lot more you could do, and they're all over the place. It's not easy to find them, and really Hubble has made a tremendous difference in our being able to find most of the binaries that have been found in globular clusters have been found using Hubble, because you need very accurate measurements, and they're faint stars. So the combination, the only binaries we could find in clusters pre-Hubble were ones that were binaries among the giant stars using radio velocity techniques, and just looking for changes in the positions of spectral lines due to the Doppler effect among giants. So, never say never. But people have looked, and so there are limits that have been placed. Yeah, I'm not going to believe that there aren't any in there until a lot more work has been done.
Dr. Cole,
Yeah.
will the Jack Webb do anything to facilitate your work?
That's a good question. James Webb is very oriented towards long wavelengths and infrared. And so from the point of view, in some ways, of course, it's a larger mirror, it'll have incredible resolution. There are definitely things we can do. But for finding white dwarfs and cataclysmic variables, which contain accretion disks, white dwarfs and accretion disks, those are very blue objects. They put out a lot of UV. We look for them typically by looking in the ultraviolet or blue. Well, JWST doesn't have that sensitivity. So it'll be, there's other science that is better done with JWST. And I think that I might myself, try to focus on things that it's better suited for. There's some kinds of binaries that we've been finding that are along the main sequence. They're just pairs of main sequence stars that look like, that track the main sequence, but are just a bit brighter. And for studying low mass main sequence stars and looking for binaries along the main sequence, that I think would be very good for. Not so much for white dwarfs and things like that. So I'm glad Hubble's going to be up for a while. They're hoping to keep it up for a bit longer. So having both and being able to do both is incredible. But that it'll be a loss to have no UV, ultraviolet, or blue sensitivity.
How about the big 30-meter telescopes they're building? Will those help?
It's interesting. We've been thinking quite a bit about what we can do from the ground. Of course, with adaptive optics, you can get much higher resolution. You can get amazing resolution. That's typically done again at infrared wavelengths, near infrared. And red giants are really bright in the infrared, and they really drown things out. So it's still not an easy problem. And for a while ago, we actually were trying hard to see if we could get a spectrum from the ground of one of these helium white dwarfs. We have one spectrum with Hubble. It's hard to get spectra with Hubble, but we did get spectra of a small number of cataclysmic variables to confirm that they really are what they are. A spectrum is kind of the key thing to kind of confirm what you're doing. And we got a spectrum of one of the helium white dwarfs, and showed kind of what we expected. But we checked, could we do this from the ground? And no, it's just they're too crowded. Now maybe once you go to a 30-meter, and if the adaptive optics gets better and better all the time, eventually I'm sure it will be possible. But so far it hasn't been, actually, interestingly and frustratingly.
Dr. Cole?
Yeah.
Shouldn't we then have a Hubble too?
That would be good. That would be really good. Yeah, I mean, it made sense for JWST to do what it's doing. So much interesting science is accessible at longer wavelengths. Obviously, when you look at distant universe, things are redshifted, so things get redder as you look at more and more distant galaxies, so that makes sense. Then all the work that's being done on exoplanets, there's a ton of work. If you work in the infrared, you can pick out, you have a much better chance of seeing the planet. So it made sense to err in that direction. You can't do everything all at once, but absolutely it would be fantastic to have Hubble 2, 2.0.
Any other pressing questions anybody has for Dr. Cole?
Yeah, Steve, are there any studies of the motions or orbital motions of the individual stars within?
There sure are. There's incredible work done now. So one of my collaborators, a guy by the name of Jay Anderson, who's at Space Telescope Institute, has pioneered this work. He has pioneered measuring the positions of stars within globular clusters extremely accurately. And what he's been able to do And he was actually working with, he was a grad student of Ivan King, the guy I did my postdoc with. So he actually pioneered doing this when he was a graduate student with Ivan King. And and let me just say, before Hubble, no one had been able to measure internal motions of stars and clusters very much. I mean, there were attempts and some things were done, but it was really, really, really difficult. And to see the motions, you'd have to measure, a cluster 1 year and then decades later to see the change. With the techniques Jay has pioneered using Hubble, within just a small number of years, you can see stars have moved. Not a lot, but they move. And so clusters have become dynamic in a way that they never were. They were static essentially static until Hubble was launched. And now they are absolutely dynamic. And it's partly in studying those motions that people can look, for example, for any indications of a central black hole, and all kinds of other things can be studied by seeing those motions. So it's really been thrilling to see them come into sort of multi-dimensional existence over the last 30 years.
I have a question about black holes globular clusters in general. Wouldn't they, since they are very advanced old stars, isn't it likely that there would be stellar mass black holes?
Oh yeah, so that's really, gosh, I'm glad you asked that question. So it depends on, so absolutely. So surely when the cluster was born, there were a bunch of high mass stars. And then when those high mass stars went supernova, they should have left behind black holes. So where are those black holes now? And so then that depends on a lot of things. Like one of the key questions is whether those supernovae were imparted a big kick to the black holes that formed or not. When this comes back to the thing I was mentioning earlier, when you look at neutron stars in the galaxy generally, which we know come from supernova explosions, many of them are moving at incredibly high speeds. And that has been interpreted to be the result of asymmetric supernova explosions, that the supernova gas goes off in one direction and spits out the neutron star in the other direction to conserve momentum. So if there were kicks imparted to those black holes when they were formed in the first few million years of the globular cluster's existence, then they could have just gotten spit right out of the cluster at the very outset. But maybe some, that didn't necessarily have to happen to all of them. Maybe some of them did stay in the cluster. And there's been all kinds of interesting theoretical work on this. And so I can't resist mentioning, because there's such a neat connection here. In fact, there's been a lot more work on this lately. And the reason for that is, I'm sure many of you have been, heard about I've been following the work on gravitational waves, right? And so that was super exciting a few years ago when gravitational waves were first discovered. What were they from? They were determined to be from pairs of black holes. The first one, I think, was two sort of 30 solar mass black holes in a tight binary. Well, where would that come from? How do you make a pair of 30 solar mass black holes? Well, one of the kind of leading theories for where those could come from is actually from globular clusters. So you make, just as you suggested, you make some black holes in the cluster. Then if they don't get kicked out right away, what would happen is they would tend to pair up. Just what I was talking about, when stars get close together, when the cluster's dense in the center, or heavy things sink to the center anyway, they'll tend to be able to sort of grab one another and become binaries. And then if they have an interaction with a third star, they get the binary gets spit out of the cluster. And so there's some love. And then, you might see it through gravitational waves, you know, a few billion years later. So yes is the answer. Yes, they should be there. They may have already been kicked out. Maybe not. Maybe they glommed together and made a more massive black hole that we still haven't seen yet. We're not sure.
But no evidence yet.
No evidence directly, so it's all indirect. And yeah, that's right. There's no known stellar mass black holes in globular clusters yet.
Or neutron stars?
Neutron stars, there are many
okay.
neutron stars. Yes, and so that's sort of why, you know, it's interesting. You think, well, if there are a lot of neutron stars, there ought to be at least a few black holes, right? And yeah, there are many neutron stars known in globular clusters, and many of them are in binaries. Many of them are these so-called recycled pulsars that are spinning extremely fast, millisecond pulsars they're called. So yeah, a bunch of those are known in globular clusters.
Anybody else? I want to thank Professor Kuhl.
Thank you for having me.
Thank you very much.
You are so welcome.
Since the meeting is over, can I ask another question?
Okay.
Since the meeting's over, can I ask a quick question? Well, I guess kind of the after meeting. Somebody asked a question on whether the geometric center of a globular is the same as the gravitational center. Is that a safe assumption to make, or is that?
Well, so I mean, so by geometric center, like if you take all the stars, or yeah.
Well, just no, literally the direct. I mean, it's a roughly spherical object, so I mean, literally the actual center of it, spatially, and that he was asking whether that would also be the gravitational center. And he was asking how you could assume that, or is that assumed?
That's an interesting question. I would say that we see, I mean, there's so many stars, right? And there's a range of masses of stars. The only reason they wouldn't be, the same is if there were kind of different masses in different parts of the cluster or something, right? Like, by geometrical center, do you mean like if you just look at where the center of all the stars is?
Yeah, literally the center of it, right?
Yeah, and so in practice, of course, what we see is stars, and so yes, we use the stars, although we try to be careful to not let the giants kind of, you sort of try to ignore the giants and look at the main sequence stars, the sort of sun-like stars, so as not to be kind of thrown off by a few bright giants. But unless there were variations in the masses of cluster stars that were different in different places, then there would be no reason. Bottom line is we do assume it. Yes, we assume it, but there's pretty good evidence that that's a reasonable assumption. But you never know when maybe things could go wrong. So it's a good thing, good question. good to question one's assumptions. Always good to question the assumptions. Absolutely.
All right, thanks.
Yeah.
Thank you, Dr. Cole. That was my question. Thank you.
Okay, you're welcome.
Is there any evidence of dark matter? Or, I mean, does the gravity of the stars explain the cluster binding together, or do you see dark matter or dark energy interactions?
Thank you for asking that. So far, it does look like stars can explain the dynamics that we see. We don't see any need for dark matter. I should say, though, that, until it's possible to get pretty far out in the cluster, it's hard to judge whether maybe in the outskirts, maybe some dark matter might have some influence. But the thing to remember is globular clusters are pretty small. You know how it's on the galaxy scale, you need to get out to, sort of large scales to have dark matter be playing a big role. So it wouldn't be surprising that dark matter, might not play a very big role. But anyway, it's a good question. It could, but so far the dynamics look like they're consistent with the stars that we see being able to explain it. Stars that we see and infer, just, very, we can see, you know, how many low mass stars there are. Maybe we don't see all of them, but we can infer how many, and then determine, you know, whether the dynamics kind of all add up based on those. And so far, it looks pretty good. Yeah.
Sorry, I have another question.
Yeah.
What exactly is dark matter? Is it like a substitute term, or?
Sorry, is it like what?
Because in some cases I hear it referred to as something like what people would use as a variable in like mathematics as an example.
Yeah, okay, great question. So dark matter is a term that's given to something that we don't know what it is yet, okay? But we believe that it exists for several reasons. The main reason we think that there's some matter in the universe whose nature we don't yet know, but that really does exist and exert gravitational force, is from looking at the way that galaxies spin. And in particular, if you know how, like, if you're on a merry-go-round, are there merry-go-rounds anymore? Ever been on a merry-go-round going around and around in a circle, and if you don't hold on, you just go flying off the merry-go-round, right? That centrifugal force you feel. Do you know what I'm talking about?
Yes.
Yes, great. Well, so the same thing happens with a galaxy. Like the stars in a galaxy, picture like our galaxy, which is shaped kind of like a disk. And the stars are going around and around in circles in that disk, and they're going really fast. And so something has to be holding them together, keeping them from just flying apart. Because when things are going fast in circles, they tend to want to fly apart. Just like, you know, if we let go of on a merry-go-round, we would just fly right off. Same thing with a galaxy, it would fly apart unless there's enough mass, enough material holding it together, sort of exerting gravitational force to hold it together. So then you can ask the question, okay, well, I mean, there are a lot of stars, so maybe they're all holding each other together. Maybe that's enough. Well, if you look at it, you discover that no, it's not nearly enough. If you add up all the stars that you see, and the ones you can kind of refer probably there, even if you don't see them directly, and then you also add the gas, there's gas, and there's stuff we call dust, there's all sorts of little things. If you add all that up, it's nowhere near enough. It's like not enough by a factor of 20 or something. So, so if there weren't some other thing that we don't know what it is yet, helping hold the galaxies together, they ought to just fly apart. So that is the biggest reason that we think there is something unseen. And this was discovered by a woman by the name of Vera Rubin in the 1970s. This was her sort of, I think it was actually maybe her PhD thesis, and certainly early career work. They're called rotation curves of galaxies. Anyway, she figured out that the dark matter would need to be present. Something, and all it means is something that we can't see, but is there. So what is dark matter? That is one of the holy grails in astronomy right now. Many people are trying to figure that out, astronomers and physicists. There are many ideas out there. Some of those ideas have been ruled out. One idea was maybe dark matter is made up of a whole bunch of like burned out stars that are just really, really faint. Or maybe it's a bunch of brown dwarfs, which are balls of gas that aren't big enough to actually be stars. They're just kind of very dim, really, really dim balls of gas that are like failed stars. They don't have enough mass to make fusion happen. That hypothesis was tested a couple decades ago now, and it's continued to be tested more carefully. And that has been pretty much ruled out. They cannot be the source of the dark matter. Current candidates are particles that but they can pass through, they pass through the Earth without you hardly noticing. Have you ever heard of neutrinos?
Actually, you cut out once you started the second theory.
Oh, I'm sorry. You know what? Let me turn off. Should I turn off my video? Maybe that. I'm going to stop my video in case that helps the audio not cut out. So first theory was maybe there's, there are these burned out stars, or maybe they're failed stars, and that got ruled out. Second theory was maybe they are some kind of fundamental particle, a tiny little particle that we don't know what it is yet. And that might sound kind of crazy, but there are such particles that we do know exist in the universe. And one kind is called a neutrino. And these are tiny little particles that, that interact very weakly with other things. And so they sail right through the Earth, for example. But we have learned, physicists and astronomers have learned to detect them. They're hard to detect, but we can detect them. We know they're there. And so maybe there's another particle like that out there, and we just don't know what it is yet. And physicists have hypothesized many different possible kinds of particles that might be the source of the dark matter. And then there's a whole bunch of physicists and astronomers who are searching for those particles as we speak. There's a woman at Columbia University, for example, I'll mention, Elena Aprile, who I worked with when I was first getting into astronomy. Just briefly, I worked in her lab, and she had, she's still doing this. She's kind of leading the effort to search for dark matter using a particular technique that she pioneered, using liquid xenon to try to detect dark matter particles. So I'm rooting for her. I hope she's the one who finds it. So,
thank you.
You're welcome.
That was the greatest explanation of dark matter that I've ever heard. Your merry-go-round analogy. Fantastic. Thank you.
Thank you.
Any more? Going once, going twice. We're going to call this meeting adjourned.
Okay.
Thank you, Professor Kuhl.
You are so welcome. It was delightful. Thank you for putting up with less than perfect electronics and video and sound and all that. I really appreciate your coming. And it's nice to meet you virtually. Hopefully sometime we can meet in person.
Thank you.
Thank you.
All right. Have a good night. Thanks, everybody.